Hello, myself, Dr. Kode Jaya Prakash, working as Senior Assistant Professor in Department of Mechanical Engineering at VJEC. So today I am going to discuss about the topic on rapid tooling and softwares used for additive manufacturing. So what is meant by rapid tooling and what are the different categories of rapid tooling and how the rapid tooling plays an important role for additive manufacturing. After completion of the topic, then I'm going to discuss about what are the softwares that are going to be used for additive manufacturing. Now, coming to the case of rapid tooling, what is meant by the rapid tooling? So as you can see that it is used to describe a process which is either uses a rapid prototyping model as a pattern. So here, generally in the subtractive manufacturing, what exactly we are going to do, we are going to make a mold, we are going to make a pattern, and based upon that we are going to cast that material, and based upon that we are going to form the entire process. But here, why we are going to use the rapid tooling is that, suppose if you want to make the complex patterns or complex shapes or complex molds, so that a replica of doing such sort of things in subtractive manufacturing is quite difficult. So this is where the rapid tooling is going to bridge the gap between the iterative tooling and as well as the design process. So this is where it is going to play an important role. So as you can see that it is a model or a pattern. It is going to be used to create a mold quickly or uses rapid prototyping process directly to fabricate to a tool for the limited volume of prototypes. So one thing you can say that it is not going to be suitable for mass production. It is going to be only for limited volume of prototypes, only for a complexity of the models, not just like a mass manufacturing. So going to make a number of models at a time. So what are the different methods of rapid tooling? As you can see that there is a cal tool process and the sprayed metal tooling and ACES tooling, and investment casting, selective laser sintering, and stereolithography. So these are the different common methods that are going to be used for rapid tooling. Now here you can see that examples of rapid tooling methods. So you can see the first one is going to make a porous metal mold. So this is made by using the rapid tooling methods, and you can see that figure B is going to show an example of there's a plaster mold made by using rapid tooling. So based upon this, we are going to make the parts. So this making of the tolerances and making of the looking after the accuracy point of view, it is quite a challenging task, especially for complexity of the models. So this is where the rapid tooling is going to play an important role. Now here you can see that this is also one of the example. As you can see, the first example, an example of a case mold developed through rapid tooling. And figure B shows that example of a sand casting mold made with the rapid tooling. You can see the complexity of the model. It's a mold. Now, what is the classification of rapid tooling? So rapid tooling is generally divided into two categories. One is direct routes and indirect routes. Direct routes, what exactly is going to happen? We are going to use the CAD file to produce the tool, and directly that tool is going to be used for manufacturing. Means that we are going to make a tool in the CAD file that is going to be made by additive manufacturing method, and that after fabrication through additive manufacturing, directly that tool is going to be used for the mass production or sort of manufacturing process. But whereas when you take the case of indirect routes, a rapid prototyping model or a master pattern, the master pattern is going to be built by the rapid prototyping model, and based upon this master pattern, number of molds are going to be established, and then finally followed with the routes, different different models of the routes are going to make it. So this is the most important classification: direct routes and indirect routes. And here, indirect routes. Now we are going to discuss about the indirect routes, how the master molds are going to be done. So as you can see that the rapid prototyping molds can be used as a master models for several applications. As you can see here, silicon tooling, it is especially used to make wax models for investment casting, and porous plastic molds for pressure casting ceramics, and case molds for bench casting, and patterns for sand casting of the metals, and wax rapid prototyping models for low cost for lost investment casting. So these are the indirect routes which are going to be used for making of the rapid tooling. And you can see how it is going to play an important role for in investment casting. So investment casting accuracy is much more required. So first of all, the pattern is going to be created by using an additive manufacturing or other sort of that is suitable for 3D printing process. Based upon this, number of patterns are going to be prepared, and finally this is going to be assembled as a tree, and then the entire tree is going to be inserted into the flask and filled with the wax, and then finally after heating and after making that, we are going to finish that molds, and then we are going to clean with water jet and fill mold with metal, and that wax melted is going to happen. So this is a sequence of making this investment casting. As you can see that in this investment casting, first and foremost thing is that pattern creation. So this pattern creation plays an important role as a simple master mold. Based upon this master pattern, number of molds are going to be prepared. Now, rapid tooling for in investment casting, mostly that pattern is going to be used for making SLA process. So stereolithography is the process which is especially used to create the pattern, and this is going to play an important role for the accuracy point of view. Where accuracy is required, then we are going to use the SLA. So the SLA is only going to suit for wax molds. And rapid tooling in action, as you can see that Invisalign orthodontic aligners. So these aligners generally they are going to make with the conventional models, especially the patient. They are going to take the impressions from the patients. But whereas this is a combination of rapid tooling and the process of the thermoforming is going to be used for much more accuracy of the process. As you can see, this polymer impression of the patient's teeth is going to be taken, and that computer modeling used to produce the CAD representations of the desired tooth profiles, because every human anatomy is going to be vary from each other. So different patients are having the different tooth profiles. So the patient specific tooth profiles impressions along with the suitable CAD modeling is going to be taken, and the model is going to be produced by using SLA machine, and then the aligner is produced by the thermoforming a transparent plastic sheet. So plastic sheet again is the model, and the patient uses aligner for 2 weeks, and then followed by the completion of the treatment. So this is where the rapid tooling in action is going to play an important role here. Now, rapid tooling and injection molding, as you can see this, injection molding especially it is used in rapid tooling to produce molds or mold inserts. But whereas here in this, a CAD mold is produced which can be easily edited, and the common use of this technique is producing molds for the slip casting of the ceramics. As you can see this part is going to be made by the injection molded product, and then a mold tool is going to be created with a mold insert, and the slip pod is going to be placed in the mold and slip drained from the mold and followed with the removal of excess metal, and then finished of the product. As you can see, that's how this CAD model and the AM is going to be used to finish the parts. Now, rapid tooling and RTV molding. So here there's a room temperature vulcanizing process. So here the tool can see here the vulcanization process. It is going to use a mixture of polymer and a curing agent. And here RTV rubber solution is going to be poured over the pattern and allowed to set. And the mold is going to be used for the injection molding. And this process, this sort of mold can be used for maximum of 25 to 30 parts. So here, the one of the main drawback is that the mold is having very low life, and rubber can be a progressive damage after it is going to exceed the certain number of parts. Now here, one more process, that is cal tool process. So this cal tool process is going to be starts by using rapid prototyping, a rubber mold, and then after that, which is going to be used to cast a steel powder and the polymer binder. So it's a combination of a steel powder and a steel powder and the polymer binder, which is going to be cured into a green state. And once it is going to be cured, and then it is fired, and copper is infiltrated, especially into the mold, by resulting in the tools 70% of the steel and 30% of the copper. And this sort of mold can be polished or machined to increase the surface finish, because especially to maintain the good tolerances, although the finishing is normally not required. It's a process of cal tool process. So this cal tool process is created over 25 years ago by 3M company. So, and this can be used to create accurate molds and mold life. You can see there's more than 1 lakh parts. You can use up to 1 lakh parts, and mold tools having the limited size of volume. It's not a big size. And companies sometimes join two Cal tool molds together to increase the mold tool size. If you want to increase the mold tool size, so there's a combination of assembly of the two molds can be used here. And the molds are especially the strong enough to withstand typical injection mold temperature in use. So this is the specialty of the Cal tool process. And here next, ACS, acetyl clear epoxy solid. So this mold can be used as inserts in the standard injection molding machine. This is widely used in the injection molding machine, and the mold is created using SLA method. And this suitable cavity on underside of the mold, and two mold halves are going to be put together, and then it's going to be filled by the epoxy solution. Epoxy or ceramics or low melt materials or the thermoplastics, and it has tool life of maximum of 10 to 100 parts. So which is having a gradually degrading with the use. More than, if it exceeds more than 100 parts, then the mold life is going to be decreased. And sprayed metal tooling, and this sort of sprayed metal tooling, the pattern is going to be finished to ensure that mold has the best quality to the specification required, and this base is then coated by using a zinc aluminum alloy. So this alloy coating and the base are going to be placed within a flask or tank, which is then filled with aluminum powder filled epoxy. So once cured, there's a base plate and the pattern is going to be removed, and second half is going to be created for injection molding, and totally it is going to complete in the mold tool. As you can see here, so this going to be made using the sprayed metal tooling, and 100 to 1 lakh uses of low pressure process yields greater to 2 lifespan. This is how this sprayed metal tooling is going to be used. And so up to here, these are the indirect routes. Now coming to case of direct routes. So this direct routes, especially the CAD model is going to be used and created to STL file, and then the concerned part is going to be prepared by using any additive manufacturing technique, and then that part is going to be used directly. So this is called as direct rapid tooling. And what are the methods that is going to be used for direct rapid tooling? Selective laser sintering. It is going to be produces the parts molds by using CAD techniques, and using you can use FDM also, FDM techniques also, FDM, SLA, and selective laser sintering. And also sometimes based upon the equipment, DMLS also can be used. So it is used a variety of materials: steel, copper, polyamide, etc. So direct tools, and in this one of the technique is selective laser sintering. As you can see here, selective laser sintering, this is a completely under a powder based AM process. The powder is going to be sintered by using CO2 laser, and the part is going to be produced, and that part is going to be taken and going to be used for the manufacturing. You can see this based upon the selective laser sintering. How this engine block is going to be made, because here the rapid tooling is going to be used. Otherwise, they're going to use for the aluminum casting. It's a huge and big process. Because of this rapid tooling, the time is cut shortened, and then you can see the accuracy of the part is also going to be increased. And also fused deposition molding, that is going to be used for limited making of the patterns. Is not that much complex profiles can't be used, and up to the limited case of patterns we're going to be used for FDM process. FDM process you can use for ABS, PLA, nylon, PPG, etc. materials. And also laminated object manufacturing also is going to be used for direct rapid tooling, especially made up of sheet materials, and most of the applications is form and fit for functions and rapid tooling patterns, where complexity is not that much required. So as you can see, this the process of rapid tooling, a three-dimensional computer model of the mold is going to be designed on a computer, and then the second step is that a plastic pattern with complementary shape to the mold is fabricated by using a certain AM process, such as SLA or SLS or any sort of the suitable technique. So a thin metal layer is deposited on the cavities on the cavity side of the plastic pattern. We're going to use an electrochemical process to form a metal shell, and metal ribs are added to the back of the metal shell to increase the strength of the metal shell. And the back side of the mold is sealed to prevent the leakage of the metal powder, and then the tool is going to be finished and ready for molding operations. And what are the advantages of rapid tooling? It is going to be reduced manufacturing time and much less expensive and effective communication and early viewing of the product and early market testing, assembly and functional testing. And what are the drawbacks of the rapid tooling? Shorter tool life, especially because the tool is going to limit it up to certain 100 or 1 lakh. That depends upon the type of metal you are going to use. And tolerance is it is somewhat low, not much tolerances you are going to obtain. And cost is sometimes it may be debatable and not suitable for large-sized applications. And the future developments of rapid tooling, the tooling is going to, the R&D work is going to be happen nowadays, especially. The tooling is going to become faster and cost is going to be gradually reduced and development time and also more accurate and faster marketing testing. And these are the applications of this RP, rapid prototyping and RP tooling as used for design and engineering analysis and planning for medical applications, especially for tooth and bone implants and hearing instruments, and also used for for the arts and archaeology, making of the statues and making of the ornaments. And coming to the case of rapid tooling applications, vacuum casting for metal spraying, and for casting used for the sand casting applications and investment casting and die casting, and also EDM electrodes, electric discharge meshing electrodes. And now, what are the softwares which are required for additive manufacturing? What are the softwares? So here, the first and foremost thing is that Materialize Magics. So Materialize is a company which is from Belgium. Belgium is a famous software which is going to be used widely for the working of STL file issues. And also this software is mostly compatible with any type of n number of formats. You can see additionally the program capabilities can be expanded up to modules, MGX, IGS format, and VDA, VRLM, CATIA, and all these sort of formats can also be used. And also this Materialize Magic software is also used for the scanning of the parts. So for because the scanning is going to be done by using UV light or blue light or some sort of laser scan is going to be done. So that data is going to be captured, and so if for the in the case of point data cloud, and that editing of the scanned patches also going to be done using that Materialize Magic software. So this complexity is going to be suited for this Materialize Magic software. As you can see this, what is the features of this Materialize Magics? There's a data, what is required for data and build, how to build the models, compatible with all type of data formats, and file repair and data preparation for all AM technologies is going to be used, and data editing and enhancement of the tools, and automated build platform making, and measurements and reporting for quality control. So these are the points which are required, especially plays an important role for the features of the Materialize Magics. So especially this Materialize Magics is going to be a leading software efficiency. It guides you through every steps in the additive manufacturing workflow. So this is the main point, especially. And coming to the case of applications of Materialize Magics in the repairing and optimization of 3D models, and if you want to analyze the parts and making the process which is related to changes on STL files, designing of fixtures, and project documentation and production planning. These are the main and common applications for the Materialize Magics. And why choose Materialize Magics? What are the features? Why it is required? It is going to be, so the platforms is going to make a platforms very easier and faster, and it is going to save the material, and also it's going to reduce lead times and repair and prepare files for all the technologies, right from polymers to till metals, and edit and enhancement of the data, and to perform the simulations. So before going to the AM itself, we are going to check and test with the simulations. And now coming to the case of there's other software. So this Materialize Magics is going to be used for the engineering applications. All the sort of points what we have discussed, what sort of format is going to be compatible. This Materialize Magics is going to be sourced only for engineering applications. But whereas what is the software which requires for medical applications? So that now before going to the medical application software, first I am going to discuss about how the role of how the role of AM is going to be used for the medical additive manufacturing. So how this additive manufacturing is going to be used for the medical applications. It's especially used for making of surgical models. In this surgical models, pre-operative planning and intraoperative guides is going to be used to going to be trials to work out on the most of the trials for the senior level of making this complex surgical complex models. And coming to the case of educational models, that is motion. So those models are going to be made by using this additive manufacturing for the patient education and learner education and surgical simulation. And medical devices, where accuracy plays an important role for medical devices, that is prosthetic applications and wearable devices, and also going to make for using implants, and also for tissue engineering, that is a scaffold based and bioprinting. So this bioprinting is that these gene cells are going to be taken inside your body. Based upon that, it is going to fill with bio ink, and based upon this bio ink, your organs are going to be printed. That is called as bioprinting. And what is the sequence? So how this AM is going to play an important role based upon, because see, for engineering applications, because we are going to use the different CAD modeling softwares like CATIA, CATIA Pro-E, or Fusion 360, etc. Number of CAD software, because to suppose, for example, to model a human parts, to model a human bone, to model a human teeth, these complex profiles can't be done by using this CAD modeling softwares. So how we are going to get those softwares? So it means that how we are going to get the data of this making of the models of the body parts. It is too complex to model with the CAD models. Now this is where the data is going to be extracted from MRI scans and CT scans, magnetic resonance imaging and computerized tomography. From that, the file is going to be saved in the DICOM format. The DICOM means abbreviation is a digital imaging and communication in medicine. So this DICOM format is going to be taken, and that is going to be processed in the medical modeling software. What is that medical modeling software? I'm going to tell you after this slide. So this based upon this DICOM format, the file is going to be converted to the STL file based upon the medical processing software whatever we are going to use, and that STL file is going to be sent to the AM machine, and virtual prototype of the model is going to be made, and then we need to select that using the concerned suitable technique, and then printing layer by layer, and then we are going to produce the part. So this is the sequence of the steps is going to be followed for the medical 3D printing. But whereas for engineering applications for the AM, first we need to go for the CAD modeling, and then we need to convert in .stl, and then we need to work out with the build parameters, etc. Here also, in the CAD is here in this medical modeling, the CAD is going to be replaced by the data which is going to be extracted from MRI scans and CT scans. And based upon that, it is going to be processed in the medical modeling software, and then it is going to be converted into STL file. And remaining process are same, just like for engineering, for AM applications. One of the thing is that extracting of the data is different from the engineering application additive manufacturing point of view. Now here, as you can see this from CT scanning and saving as DICOM format, and this DICOM is compatible software using that image segmentation, what are the body parts which are required, then we are going to perform this image segmentation, and then suitable STL compatible software is going to be taken, and based upon that, this working of mesh editing, cleaning and smoothing process is going to be done, and that file which is going to be processed in the medical software is going to be sent to the 3D printer and polishing and cleaning, and then it is going to be used. And you can see this, the patient, this is how the process is going to be done. Patient CT scan is going to be obtained, and then this processing of images by using my medical modeling software, and this is called as region of interest. There's ROI. Suppose if you want only this jaw, and this remaining entire process is going to be removed and processed in the medical modeling software, and the portion of the jaw it is going to be left over, and then that is going to be printed, and then based upon the patient, because the physical model is going to obtain from the patient, because otherwise the doctors has to do the number of iterations from this X-ray and CT scans. But here the main advantage of this additive manufacturing in the medical is that the complete physical model as per the dimensions is going to be obtained using the AM machine. So based upon this, the exact implant dimensions is going to be made by the doctors, and then the concerned implantation is going to be done, and then it is going to be inserted into the either patient body, etc. So this is where it is going to improve the success rate of complex surgeries. So this is why this medical additive manufacturing is going to place an important role for the complex surgeries. And one such software it is going to be used is Materialize Mimics. So this is a Materialize interactive image medical image control system, and this is going to be compatible obtained from the data from CT scans and MRI scans and micro CT and CBCT and ultrasound confocal microscopy. So here from this sort of data, that is a 3D surface model, and from stacks of 2D imaging data. So these 3D models uses a variety of engineering applications, and these patient-specific models are going to be used for variety of engineering applications to apply for the CAD and CAD and FEA packages. So means that this sort of DICOM files is going to be processed in this Materialize Mimic software. And what is the applications where it's going to be used for industrial application? There is a cardiovascular and craniomaxillofacial and orthopedic and pulmonology. So these are the common industries which is going to be used with the Materialize Mimic software. And what is the application of Mimics? Especially the 3D measurement and analysis, and computer-aided design, and computational fluid dynamics, and customized implant design, and rapid prototyping. All this sort of systems is going to be support for this EOS and Stratasys and 3D systems, Z Corp and etc. And also used for surgical simulation. So thank you. So this is about these topics of rapid tooling and software used for medical 3D printing. Thank you. Thanks a lot.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.